All right, let's talk about AI. In this field, the race is always for bigger, more complex models, right? But what if I told you a model so small it could literally fit into a single tweet could outperform them all? Well, today we're diving into a piece of research that does exactly that. This is going to be fun.
Take a look at this number, 180 bytes. That's the entire size of this machine learning model. To give you some perspective, the text of a simple tweet is bigger than this. And yet this unbelievably tiny model can analyze huge satellite images with stunning accuracy. It's kind of mind-blowing.
So that's the big mystery we're going to solve today, right? How in the world did a team of researchers build a classifier that's just dwarfed by these massive models, yet still manages to come out on top?
To really appreciate just how brilliant the solution is, we first have to get our heads around the challenge. The mission is to take a super high-resolution satellite image and figure out what's on the ground. Is that patch of forest? Is this a city? Or is that a lake?
And believe me, this is way more than just an academic puzzle. This kind of classification is absolutely critical for the real world. We're talking about planning how our cities grow, managing precious natural resources, or even how we respond to disasters. It's all about turning that raw data from space into knowledge we can actually use.
And this is the secret sauce. The clever technique at the heart of it all is called the Neighborhood Median Pixel Method, or NMPM for short. The core idea is actually super simple, but it's incredibly powerful. Instead of just looking at one pixel all by itself, it looks at its local neighborhood, working on the pretty solid assumption that a pixel is probably the same type of land as its neighbors. Makes sense, right?
Okay, now this is where the story gets really good. Before NMPM came along, researchers were throwing these huge, complicated neural networks at this problem, and honestly, the results were pretty disappointing. Then along comes this tiny 180-byte method, and bam! It hits over 94% accuracy right out of the gate. So the question is, what was its secret?
Now that high performance was no lucky accident. Nope. It was the result of a really dedicated search for accuracy, where these researchers just systematically built on what came before and fine-tuned the method over time.
So here's the play-by-play of how it works. For any one pixel, the algorithm looks at all its neighbors. And it does this across 10 different spectral layers. You can think of these as different ways the satellite sees the world, like in infrared. For each of those layers, it finds the median value of the neighborhood. Then, it gives a score based on how typical that median is for each possible class, like water or vegetation. The class with the highest total score across all 10 layers wins. Simple as that. But the real genius is in the scoring.
This slide really gives us a peek under the hood at that scoring logic. Basically, if a neighborhood's median value is a perfect match for a class, it falls into that strong similarity zone, it gets a really high score. If it's close but not quite perfect, it gets a decent score, and if it's a terrible match, it actually gets a penalty. And you could see on this timeline how that accuracy just kept climbing. It started by beating an older technique. Then the first version of NMPJam jumped it up to 94%. Then the researchers found that looking at a slightly bigger neighborhood worked even better. And finally, they used optimization algorithms to tweak the scoring system and pushed it even higher.
But, as the accuracy was climbing, there was this one nagging question that the researchers couldn't shake. The scoring system worked amazingly well, but it was based on these numbers that, well, they seemed like they were chosen completely at random.
The scores were set at 14, 4, 1, and negative 14 for the different levels of similarity. But why those specific numbers? They felt so arbitrary, but the results were just undeniable. Solving this little puzzle was what led to a massive breakthrough in understanding what made NMPM so powerful.
And this slide right here, this illustrates that aha moment perfectly. The researchers discovered the system was invariant. Basically, that means the specific numbers they used for the scores didn't actually matter. As long as the relationship between the scores was the same, you could add a constant to all of them or multiply them, and the final classification would be identical.
So the huge takeaway here is that the relative difference between the scores is what does all the work, not their actual values. I mean, this was a total game changer. It simplified the problem like you wouldn't believe. They weren't hunting for 4 magic numbers anymore, they just needed to find the perfect relationship between them.
And that insight led to a way smarter way to optimize the whole thing. By using this idea of invariance, the researchers could just lock the penalty score at 0 and the weak similarity score at 1.
And now, their optimization algorithm only had to solve for 2 variables instead of 4. It made finding the perfect scores so much more efficient.
And just look at the payoff. It's so clear. This smarter way of optimizing pushed the accuracy even higher, all the way to 97.5% for the best neighborhood size. That's a real, tangible improvement that came straight from a deep theoretical insight. So cool.
Okay, so let's wrap this up. What makes this tiny classifier so darn effective? Well, it all boils down to a few core ideas that are just beautiful in their simplicity, but incredibly powerful when you put them together. First, it uses the neighborhood context. Smart. Second, using the median makes it super tough against noise and weird outliers. Even smarter. Third, it works with the real, messy data we have instead of assuming some perfect statistical model. And finally, it builds a really strong case by pulling in evidence from all 10 of those spectral layers.
You know, the researchers' own conclusion really says it best. They call NMPM a lightweight yet powerful classification approach. It's just a perfect example of how really clever design can beat brute force complexity any day.
And that brings us to our final thought. In an age that's so dominated by these gigantic AI models, the story of the 180-byte classifier is just this amazing reminder that sometimes the most elegant and simple solutions are the best ones. It really makes you wonder, doesn't it? What other simple, brilliant ideas are we overlooking right now? Thanks for joining us.